next to the last class. As usual, I'm talking a lot, and I'm behind my original schedule, but we'll make sure we have everything covered for the exam and everything covered. So this is the next to the last class for this group that I'll be teaching. Next week we'll have another class. I should be back in my office, my home office next week. I also go back to my own university next week too. So next week's going to be a rather busy week for me. We'll talk about the exam next week. The exam is going to be between Rosh Hashanah and Yom Kippur. I think if the memory serves me right, it's around the 14th, but I don't remember the exact date. I'll look it up and make sure we have all the dates there. So we have a lot to cover. The other thing is I don't really have a good mouse or anything with me here. I just have what's on my laptop. So I'm not going to be right. I won't be doing as much scribbling as I have in the past. I'll be, but we'll see what I can do. So let me start already with see what we can do here. Let's start where we left off last time.
Professor Zelensky?
Yes.
Sorry, it's way off here and here also.
Oh, okay. Now you're back. I saw you for a second, your name pop up, and then you disappeared. So
yeah,
now,
yeah.
okay, I got you.
Okay, thanks.
Rima Lerner also.
Oh, Rima, okay. So let's see, who am I missing? Yogev Becher, Yogev, are you there? And Ron Matskin. Okay. So the only two I don't have are Yogev Becher and Ron Matskin. Okay, very good. Okay, so what I want to talk about now is I want to sort of finish up Rail in the next 15, 20 minutes, which for me probably means it's going to be a half hour. And I want to get into track train dynamics and geometry. We can get to it today. So we talked about fatigue defects and the theory behind fatigue defects, and we showed you all sorts of fatigue defects. And the issue with fatigue, wear is fairly uniform. If you have a curve, the curve is more or less going to wear the same. So when the curve reaches its wear limit, you're going to replace it, and that's the end of the business. You replace at the wear. Fatigue functions a little different. Let's say I have a kilometer of track, and I have a fatigue defect that pops up. I'm not going to replace the entire kilometer of track for one fatigue defect. I'm going to go in there. I'm going to cut out that one defect. They actually showed that in that Network Rail movie, if you recall. I'm going to cut off, somewhere between 12 and 15 meters of rail. Sometimes even less. In some properties, you may be cutting off 6 or 7 meters of rail, and you replace the defect with a new piece of rail, and the rest of the rail you don't touch. And then next year, another defect pops up, and you do the same thing. And the next year, another defect pops up, and you do the same thing. And the next year, 3 more defects pop up. And at that point in time, you start considering, wait a minute, maybe I should start considering replacing this kilometer of rail. Because you don't, what happens is, if you remember, there's a risk of that defect not being found. There's about 90% of the defects are found by ultrasonic testing. Of the remaining 10%, 99% of those are found by track circuits or something like that, or inspectors. And but there's a population of defects that results in a derailment, just like the network rail derailment I showed you. These derailments happen all over the world, broken rail derailments. It's a major cause. So what we want to do is we want to at some point think about replacing the rail if the defect rates get very high. And we usually think in terms of replacing the rail in terms of defects per kilometer per year or defects per mile per year, depending on which world you're living in. Obviously, you're in the metric world, so it's defects per kilometer per year. Typically, when you start getting about 3 defects per kilometer per year, you really got to start seriously thinking about replacing the rail. So the obvious question is, do you sort of just want to wait until you start getting 3 defects per mile per year? So you see 3 defects in a year in a kilometer, or so if I have 10 kilometers of rail and I see 30 defects in that 10 kilometers, do I start thinking about replacing it? Or do I want to be able to look ahead and predict when those defects are going to occur? If, as long as I have an ongoing development of small number of defects, can I project forward and see the rate of failure? And that is what the purpose of the Weibull equation is. The Weibull equation is designed to allow us to predict the growth of defects. And it's based on defect growth theory that's actually fairly universal. The Weibull equations were originally developed for in the biological sciences, and then they were later applied to structural steel and structural steel defects. And around the 1970s, 1980s, they started to be applied to the railway industry. And we found that we can start predicting the rate of development of fatigue defects using this type of Weibull equation. So the Weibull equation is basically think of it as plotting your development of your cumulative number of defects plotted on a log-log scale. So this is a log-log scale, where the horizontal axis, the x-axis, is the total cumulative tonnage at the time the defects develop, and the vertical axis is the probability of the defect occurring, and I'll explain that in a couple of minutes. So the probability of a defect occurrence is on the vertical axis. The tonnage at which the defects occurs is on the horizontal axis. And then if we start plotting the development of defects, it actually comes out on a log-log, on a linear straight line on the log-log curve. So each one of these points is the cumulative probability. So this is the very first defect. So if I'm looking at a section of track that has 1,000 segments of rail, and I'll define that in a little bit better in a few seconds. But if I have a piece of track that has 1,000 segments of rail, so this is 1 in 1,000. Actually, this is 10 to the minus, it's 5 times 10 to the minus 3. So this was probably maybe 2,000 segments of rail. 1 out of 2,000 would give me 5 times 10 to the minus 3. This would be 2 out of the second defect. So 1 plus 2 is 2. The third defect, the fourth defect, the fifth defect, the sixth defect. And we keep plotting them. And that gives us the straight line. And this straight line on log-log curve. And this straight line is defined by 2 parameters: the slope, which is defined as alpha. So alpha is the slope of this line on log-log, and the intercept. Now, instead of the traditional intercept of 0 that you normally use, in Weibull equations, we calculate the intercept to be at the 63.2% point. That's the definition that Weibull uses for the intercept. And the MGT value that occurs at 63.2% cumulative probability is the beta value. So we have alpha and beta. So we can take now this relationship, this graphical relationship, and we can actually develop an equation, because since it's on a log-log scale, it's obviously exponential. So the cumulative probability, the vertical axis, is equal to 1 minus e to the minus mgt over beta to the alpha. where P is the cumulative probability of defects occurring in a single rail. And a single rail is defined for this mathematical purposes as being 12 meters in length, or 39 feet. MGT is the cumulative MGT. Alpha, as I said, is the slope of the Weibull curve, and beta is the MGT value of which 63.2% of the rails contain a defect, or the P is equal to 0.632. And just to show you real world data, this is data taken from actually 4 different railroads. And again, this is probability in the vertical axis, MGT in the horizontal axis. And you can see the data actually follows very, very nicely on this Weibull relationship. 4 different sets of data, all showing this behavior. Okay, so let's figure out, first of all, how to calculate the probability. Okay, so this is some actual data taken from a railroad in Canada, the Quebec Cartier Mining Railroad. And what happens is we took about 86.8 kilometers of track, which was the length of that entire railroad. It's a short mining railroad. Now, 86.8 kilometers of track corresponds to about 14,000 rails, where each rail is 12 meters in length. So you take 86.8 kilometers, multiply it by 1,000, multiply it by 2, because remember, you have 2 rails. So now we're talking, so you have 1 rail on each side of the track. So you take your 86.8 or your 86,800 meters times 2, and you divide that by 12, and you get this roughly 14,000 number of rails in the segment. So this is a trace of the defects that occurred along this 86 kilometers of railroad over a period of probably, this was a period of probably about 7-8 years. So the first defect happened at 0.5 MGT. So that was the first defect. And since it's the first defect, the cumulative defect is 1. And so the probability is 1 divided by 13,945, which is 0.00007. A second defect occurred at 1 MGT. And that was the second defect, right? Because we have 1 plus 1 is 2. So 2 divided by 13,945 gives me 0.00014. At 6 MGT, 2 defects appeared. So we have a cumulative number now of 4. 1 plus 1 plus 2 is 4. And we take 4, we divide it by 13,945, and we get 0.0029. And we keep doing this for all the defects. So until you get a plot that looks like that.
Excuse me, what is the PD?
PD is the cumulative probability, which is obtained by taking the total cumulative number of defects divided by the number of rails. So in this particular case here, for example, my cumulative defects is 4, right? I had 1 plus another 1 plus another 2. So I have 4 cumulative defects. I take 4, I divide it by the number of rails in the segment I'm looking at, which is 13,945, and that gives me 0.0029. And so I can come back here and I can plot it. I can plot it on this graph.
Okay.
And I plot each of my defects. So for example, let's take at 100 MGT, I had 25 cumulative defects. That's 0.0018. So there's 100 MGT, and there's 0.0018. So you can see that data point right there. And so with this, once I define this equation, I can predict forward when I have a cumulative number of defects. So to give you an example, I have a rail, I have a line, and I know from analysis of the data already that the alpha is 3 and the beta is 2000. So again, remember the alpha is the slope of this line and the beta is the 63.2% intercept point. And so I know that alpha of 3 and beta is 2000. So I want to know what's the probability of having a defect at 1000 MGT. So I want to project out and see what's my probability of having a defect. So MGT, so I go back to my equation, P equals 1 minus E to the minus MGT beta to the alpha. I use MGT equals 1000, alpha equals 3, beta equals 2000, plug it into the equation, and I get a probability of 0.1175. What does that mean? Okay, well, that's the number of cumulative defects per that's the number of cumulative defects in that length of track. If I have 166 rails per kilometer, so excuse me, this is 0.15 is rails per cumulative rails in the entire section track. If I have 166 rails per kilometer, which is what I normally get, if I take 1,000 meters in a kilometer, right? Multiply it by 2, divided by 12. I'm going to get 166. So if I take 166 rails per kilometer and I multiply it by this cumulative probability of 0.1175, I get 19.5 defects per kilometer. So that's now that's a physically meaningful number. It gives me the number of cumulative defects per kilometer at 1,000 MGT. So I can look at 2,000, 3,000, 4,000. I can predict forward. The problem with using cumulative defects, though, cumulative probability, is it implies that I have every defect from the start of the life of the rail onwards. And unfortunately, most railroads record keeping aren't that great. So cumulative probability is a very difficult number to use because it's hard to get the cumulative probability. So a little bit more easy type of number to deal with is what we call the defect rate, or the first derivative of the probability equation, which is the defect rates, or the number of defects per kilometer per year, or the defects per kilometer per MGT, some sort of reasonable number. Now, defects per kilometer per year is actually a very easy number to use because you usually have fairly decent inspection records in current time. Most railroads now have pretty good defect records. So if you look at the last 12 months, so let's say you pick a section of track that's 50 kilometers long, and you look in the last 12 months, and you see over the past 12 months, I found 100 defects in that 50 kilometers in that 1 year period. Then I have 100 divided by 50, I have 2 defects per kilometer per year. So that's a number that's a little bit easier to work with on a practical basis. So, so we tend to work like that. Now, the other thing that happens is, remember, the Weibull plot is linear on log. If we take the first derivative of that, we actually get an exponential curve on a normal axis. So this is my defect rates, and this has defects per mile per year, but you can just as easily use defects per kilometer per year. And this is my cumulative MGT, and you can see my defect rate plot. Now you see a couple of things, not the least of which is the fact that the defect rate is nonlinear. which is something we see, and which matches the cumulative probability plot on log-log, because it's log-log. So the older the rail gets, the higher the rate of defect development. And this is what we see in real world. So we therefore have a Weibull rate equation also available, which is the first derivative of that. And that is the Weibull rate is equal to alpha over beta to the alpha to the MGT to the alpha minus 1. Where lambda now is the rate. P is the cumulative probability, lambda is the rate, everything else the same. Alpha is the slope, beta is the intersect, MGT is the cumulative MGT that of interest. So let's do an example. So we have the same rail line that we had before, alpha equals 3, beta equals 2000. I'm now giving you an extra piece of information which you want to know, which is the annual traffic density of 25 MGT. So I want to know, again, at 1000 MGT, same problem we had before, what is the defect rate now? What is the slope of the cumulative probability curve? How many defects per mile per year or how many defects per kilometer per year am I going to get at 1000 MGT on this line? Okay, so I calculate lambda using the equation I just showed you, alpha over beta to the alpha to the MGT to the alpha minus 1. So the lambda comes out to be 0.000375. And I want to convert that now into defects per mile per year or defects per kilometer per year. Let's work on defects per kilometer per year. So I have 166 rails per kilometer. That hasn't changed. A kilometer is 1,000 meters times 2 rails on a track divided by 12 meters is my defined length. And that gives me 166 rails per kilometer. My tonnage is 25 MGT short tons, which is 23 MGT metric tons, which I'm going to call MG tons here. So I take my 0.00375, which is defects per rail per MGT. So this is in defects per rail per MGT. I multiply it by 166 rails per kilometer, and I multiply it by 23 MGT per year, and I get 1.5 defects per kilometer per year, which is a very realistic type of number. So going back to the 50 kilometers of track that I had before, it means that I'm going to get in the 50 kilometers of track. I'm going to find 75 defects at the point when it reaches 1,000 MGT. Does everybody follow what I'm doing here?
Yes. Can I have a question?
Yes. You had a question, you said?
Are we talking about the 2 sides of the rail?
Are we talking about the what?
It's 1.5 defect per kilometer of rail, but it's for the 2 sides of the rail.
Yes. Yes.
Okay.
This is both sides of the rail, correct? Because remember, I took 166 rails per kilometer for 2 sides.
Okay.
So let's do a similar example at MGT of 600. Alpha equals 3, beta equals 2000. My lambda, which I just stick into the equation, is 0.000135. I multiply that by 166 rails per kilometer and 23 MGT per year, and I get 0.5 defects per kilometer per year. So that would be about 25 defects in a 50-mile segment of track. And that's not a particularly onerous number. That's a number that we have no trouble living with. So you can see in this particular plot, which is also for alpha equals 3, beta equals 2000, you can see that about 1200 MGT, I'm about 2.5 defects per kilometer per year. that's a point where I start thinking about replacing the rail. So how would we use this on a practical basis? Okay, so where you replace the rail, by the way, is a question of risk and economics, because there's a cost associated with keeping on replacing the rail. Pulling out a plug and replacing the rail is an expensive proposition. You have to increase your inspections as your defect rate gets up. You have a risk of derailment. So somewhere between 2 to 3 defects per kilometer per year starts getting to the point where people start thinking the defect rate is very excessive. Well, how do I use my equations to predict forward? So again, I have enough data, so I know what my alpha and my beta is. I'm going to keep the same alpha equal 3, beta equal 2000. My MGT is 25. Rails per mile is 271. Rails per kilometer is 166. So you can see I can start looking at what the defect rate is at 500. I'm about 0.63 defects per mile per year. My internet connection is stable. I'm going to ask anybody who has a video on to turn the video off, because I just don't want to run into a problem with stability. And I'm going to actually stop my video as well, because I just got a message saying my connection is unstable, and I don't want to lose it. So just turn off your videos if you have your videos on. Okay, so at 500 MT, I'm about 0.63 defects per mile per year, which is about 0.4 to about 0.4 defects per kilometer per year. At 700 MGT, I'm about 1.43 defects per mile per year, which is about 0.8 defects per kilometer per year. At about 1,000, I'm about 2.5 defects per mile per year, which is about 1.5 defects per kilometer per year. At 1,500, I'm about 5.71 defects per mile per year, which is about 3.2, 3.3 defects per kilometers per year. So somewhere in this zone, I'm going to go past 3 defects per kilometer per year. And so if I'm projecting forward, if I'm trying to figure out when I need to think about replacing the rail, it's going to tell me I need to start thinking about replacing the rail somewhere between 1,000 and 1,500 MGT. So why is this important? Because you just don't go out and replace 10 kilometers of rail or even 1 kilometer of rail. Number one, you don't have the rail available. You know, nobody keeps a couple of kilometers of rail sitting idly by. At least it shouldn't be. It's pretty expensive. Number two, you need to have the track time. You need to have the equipment. You need to have the gang. It's a big job to replace a kilometer of rail, and so you need to plan this in advance. And so if I can predict forward when my defect rates are going to require me to replace the rail, I can plan instead of react. And that provides me with a much safer railroad. And that brings us to the question of when should I be replacing rail? Okay, there are several major criteria for replacing rail. If you're in jointed rail territory, excessive number of rail failures or excessive batter of the rail joints is the most dominant reason for replacing rail. And I said this, I think, the other day when we talked. If I have welded rail, my two main criteria are wear and fatigue. So fatigue, wear is usually kicks into place on curves. Usually fatigue will override wear on straight track, not always, but many times. because on straight track I have head wear or top wear, but in curves I have side wear, and that tends to dominate unless I do a good job of lubrication or unless I put in a good premium steel, in which case rail fatigue defects start developing. So when do we replace rail due to fatigue? As I said, internal defects, this has 3 to 5 defects per mile per year. This is 2 to 3 defects per kilometer per year, is where people use, even though I will tell you, I have seen railroads push this out significantly, where it's going from 5 to 8. I've even been involved in studies where I found rail defects in the 10 defects per mile per year or 6 defects per kilometer per year, even though, to be honest with you, that scared me greatly because the risk of derailment is pretty high. Now, one of the things you can do to extend the life of the rail, to keep pushing out when you replace the rail, is increase your rate of fatigue test of rail testing, so that if you have 3 defects per kilometer per year, you may want to be testing 3 to 4 times a year. If you have 5 defects per kilometer to year, you want to be testing 5 to 7 times a year to make sure that you don't have any defects developing in between. Okay, so the obvious question is, do I have any choice besides replacing the rail? Because replacing the rail is very expensive. And the answer is, there's a limited number of things you can do with rail. Rail is not the easiest thing in the world to work with because it's strong, it's hard, and it's very dynamically, it's not an easy component to work with. So pretty much my major criteria, my major maintenance options for rail, other than replacement, is lubrication, which controls wear, and rail grinding to control the development of fatigue defects. So let's talk very briefly about rail grinding. And I think I've mentioned this before. Israel Railroad a couple of years ago bought a brand new rail grinder from Placer. I think it was 25 million euros. It was supposed to have been delivered 2 years ago. Actually, since I haven't been to Israel the last 2 years, I actually don't know whether it was delivered or not. I don't know if anybody out there knows whether it was delivered or not. Yes.
The machine cost 13.7 billion.
Oh, okay.
Have 24 stones.
Yes.
Tangent track and turnouts.
Right.
And
has it been delivered yet?
The manufacturer is Speno.
Oh, the manufacturer Spino. I'm sorry, you're right.
Yes, Spino. It's okay. It's okay.
I said Placer.
The machine was delivered a couple of weeks ago.
Oh, it was just delivered.
Yes, because of COVID-19, it was
that's what I heard.
Delivery. But I have a big question.
Yes.
A particular question: how to deal with grinding from standard transversal profile to the anti-head check profile in a smooth geometry.
Okay, that's an entire course.
Yes.
2.5 years ago, I think it was 2.5 years ago, I was over in Israel Railways giving a course on just that.
Yes.
Dennis Yurloff was in that course.
It's still an open issue.
Okay.
The transition between the standard transversal to the anti-head check.
That's a major discussion area, and that's something that we definitely have to talk offline. But,
exactly, because it's working very fine with in the computer world, in the 3D modeling, yeah.
Yes.
In the grinding,
it doesn't work quite as well.
it's a amount of material to take out in the gauge corner.
Okay, all right. So we're not going to get into that level of detail in this class at all. Like I said, I give a 3-day class, so that's 22 hours on that subject.
Mm-hmm.
And by the way, have you seen a copy of my book?
Yes, of course.
Okay.
I have
all
it
right.
translated the same in Hebrew. Yeah, I have all your courses.
Okay, so just so
Fine.
people, just to tell the rest of the class, I actually have a book that I wrote a number of years ago called The Art and Science of Rail Grinding, which is about 500 and something pages long and deals nothing with rail grinding, or nothing but rail grinding. Okay, so let's continue that discussion offline, but unfortunately, there's not a quick answer to that.
Thank you.
As an aside benefit, I want you to know that I was involved with the first rail grinder ever brought to Israel, which was like must have been 15 years ago. Right now, it was a contract grinder from Harsco Rail, I think it was, or one of its predecessor companies. And I remember taking it down to Allan-15 in the middle of the potash line down there and running it for the first time in Israel. But that goes back a long time. That was in the days of Professor Dr. Krug, if any of you ever remembered who he is. He and I worked together for the first rail grinder. So sorry, so the grinder cost 13 million euros. So I was off. But it's a small grinder. So he mentioned the 24-stone grinder. What you're looking at right now is a 96-stone grinder, which is about a half a kilometer long. And each one of these little sparks is a grinding motor. So this is another 96 grindstone grinder. So what a grinder does is it uses a rotating grinding stone. So when it says 96 or 24 stones or 48 stones, we have the largest grinders around are about 120 stones. The smallest grinders around are around 12. 24 is still considered on a relatively small size. But that means each one of these motors, this is one grinding motor or one grinding stone. This is the rail over here. And you can see from the stone, it's grinding on the flat of the stone. So it's not like a traditional hand grinding, which grinds on the edges, but it grinds on the flat of the stone. So this is how it grinds. So this is the grinding motor up here. This is the grinding stone. This is a consumable. This lasts on the order of about a day. So if you have a 96 stone machine like this one, that means every day you're replacing 96 stones. These stones. That's probably one of the biggest expenses of a rail grinder. And you can see how it grinds on the flat side of the stone. And what one grinding stone produces is a facet that looks like this. You can see the grinding marks. And this is about, I don't know, up here is probably about 8 millimeters, not 10 millimeters wide up here. You can see this doesn't cover the railhead. So this is one stone. So to cover the railhead, I need multiple stones, which is why I have 24, 48, 96. It determines how much coverage I have and how much metal I remove. And by rotating the grinding motor, so you can see here, I'm changing the angle of the grinding motor. I change the position of the grinding facet on the top of the railhead. So again, this is the top of my railhead. This is my gauge side over here. This is my field side over here. And you can see a 0 stone is not quite down the center. 0 is when the motor is perfectly vertical. But remember, the rail is canted. that a 1 in 20 cant on the rail gives you about 1.5 degrees of rotation. So if you have a zero motor, it's off. You're off a little bit from the dead center of the railhead because of that 1.5 degree rotation. You can see this is where a 19-degree motor goes. This is where, you know, if I had a 25 motor, I would go over here. If I had a 32 motor, I would go over here. Okay. Okay. This is a -4 degree motor, which means it's out towards the field side. The normal convention is plus angle is towards the gauge, minus angle is towards the field. And by having a distribution of motors, which we call a grinding pattern, by distributing the motors across the railhead, I can get, first of all, coverage across the entire railhead. You can see the individual facets. You can see there's a facet here, there's a facet here, there's a facet here, there's a facet here. And also by putting multiple motors on top of each other, I can take more metal off from one location than another location. And I do that to control the shape or profile of the railhead. Now, I'm not really going to get into that in any great detail here because we have way too much things to cover. But as I said, I actually give a 3-day course, which I've actually given to Israel Railways a couple of years ago, and I've given around the world, multiple railways, both U.S., Europe, Asia, everywhere, and it's a very effective technique for controlling fatigue defects, as I'll show you in a few minutes, because what you're doing is you're controlling the wheel rail contact. If you remember the wheel rail contact that we were talking about earlier, and I was showing you those pretty photoelastic slides. So if I have excessive contact over here, I can grind off some of that metal and switch it from a 1-point to 2-point contact and control the stresses at the wheel rail interface and therefore control the development of fatigue defects. So all that boring theory that I throw at you actually has some very practical uses in the real world. So in addition to internal defects, rail grinding also controls surface defects, such as corrugations. Everybody grinds corrugations. So there are grinders for metros. They're out there to grind corrugations. There are grinders for light rail or trolley track. There are production grinders. So grinders are very effective in removing surface defects such as corrugations, gauge corner spalling, engine burns in the top of the railhead, etc. Now, you also can control internal defects by controlling the wheel rail contact. So there are a couple of different ways to grind. And again, we're not going to get into this in any great detail, but traditional grinding is a very slow maintenance operation where you grind and you grind multiple passes. So each pass is every time you grind over the rail, you turn around, you come back, you make a second pass, you turn around, you come back, you make a third pass, and you're grinding at very low speed, 6 to 14 kilometers per hour. That's sort of the traditional defect grinding. Some of the new generation grinding trains have a high-speed capability that allows them to perform what's called preventive or maintenance grinding. So in traditional grinding, you're taking off about 1/4 to 1/2 of a millimeter per grinding operation. So you're taking off a lot of metal because you're trying to get rid of the corrugations, you're trying to get rid of the defects, whatever. In maintenance grinding, you're coming in there much more frequently, and you're just taking off a much smaller amount of metal and trying to control that wheel rail contact better. So you can be grinding in the order of about 0.2 to 0.3 millimeters, and you can be grinding at speeds of up to 20 kilometers per hour. Modern grinding, the fastest grinding machines out there probably go up to about 30 kilometers per hour, but that's about it. And that's a very, very high speed grinder. The faster you go, the less metal you remove.
So grinding is the opposite from lubrication?
It's not the opposite, but lubrication is designed to, but yeah, in a sense, yes. Grind, yes, I think you can use that. A lubrication is designed to prevent metal from being removed, exactly. And grinding is designed to remove metal. And but it's a different mechanism. Lubrication is focused on wear. Lubrication doesn't do anything for fatigue defects.
Okay.
And as a matter of fact, lubrication allows the development. If you remember that example I gave you before, where I said the rail was wearing away in 100 mgt, and so there were no defects or anything because it just wore away much too quickly. Once I lubricated and I slowed down the rate of wear, that's when the fatigue defects develop. So you lubricate to control wear, you grind to control fatigue.
Okay.
And let me show. Let me just end with this one, and then I have to keep going elsewhere. This shows you. This is actual data from this is a major U.S. railroad with about 40,000 kilometers of track. This is about half the track. This is about the mainline track. So you're looking at something of the order of 20,000 kilometers worth of data. And so this is the entire railroad system, a defect rate, defects per mile per MGT. So the purple line over here represents that part of the railroad that was not ground. And this represents that part of the railroad that was ground. So this was about half the railroad. This was another half the railroad. Why didn't they grind the entire railroad? Expense, availability of grinders, low tonnages. These were lower tonnage lines. These were higher tonnage lines. So higher tonnage lines would tend to develop defects much more quickly. But you can see, and just in very broad terms, you can see that the rate of defect development on ground track is about half the rate of defect development from unground track. And that's and this we see that for both tangent and curved track. So again, this was the entire railroad. I could put tangent curves together. Here we separated out tangent curves. Again, this is no grinding. By the way, you see the sharper curves. This is a degree of curvature. The sharper curves have a higher defect rate development than the shallower curves, which is consistent with reality. And this is what we also saw in this line. This is where grinding started, right around 1983. So this is a very old slide. But this was another major U.S. railroad where we looked at the introduction of rail grinding, and we very quickly saw a reduction in defects by about a factor of 2 over a period of about 3 to 4 years. On this particular railroad, by the way, we also saw a reduction in broken rail derailments by a factor of 2 as well on this particular railroad. Okay, so I'm going to leave.
Can I ask you a question?
Yes, I'm going to ask for questions now before I leave the subject. Yeah.
What is the main reason that due to grinding you have less defects?
Okay, remember we talked about fatigue as being cumulative damage. Remember I went through the entire cumulative damage theory where we calculated the number of cycles to failure, and we said you needed 2 million cycles at one stress, 500,000 cycles at another stress, but it's always multiple cycles of loading. So what happens with grinding, 2 things grinding does. Number 1, it changes the wheel rail contact geometry. So it actually reduces the contact stresses at the top of the railhead. So when I reduce I reduce my stresses, I move back up the SN curve. So my number of cycles to failure go up. So at higher stresses, I need fewer cycles, fewer MGT to fail. If I reduce my stresses, I require more cycles to fail, so that's a higher MGT. That's one. The second thing it does is I accumulate this fatigue damage in the top of the rail. If I grind off some of that rail, I am grinding off, I'm removing the rail that has a lot of cumulative damage, and I'm running on new rail that has less cumulative damage. So I'm actually removing some of the more highly damaged metal and running on less cumulative damage metal. So both those factors go into play. And we see this when I started in the rail grinding world, which is in the early 80s. I was involved with the first automated grinding machine that allowed you to run down the track and change patterns and do everything. That was in 1982. I developed the initial patterns for that. I was involved in development. In those days, nobody ground. The grinding was a sleepy little industry. There was maybe, the entire market for grinding in the world may have been, may have been in a couple of $1 million at top. It wasn't very much. After we developed the concept of rail grinding, profile grinding, controlled defects, the grinding industry boomed. And now the grinding industry is of the order of $200 to $300 million a year. Every railroad in the world grinds it. There's a little bit of difference in grinding philosophy between lighter axle load railroads and heavy axle load railroads, but that's taken into account by the stress theory. Again, I got to talk about that in my book. There are a lot of people out there from Spino International. Spino International is one of the largest providers of grinding equipment in the world. Loram is another major provider. Harsco is a third major provider. The Russians used to be in that business for a while. I think they still produce some grinders, but they're not as active internationally as people like Spino. So did I answer your question?
Yes, thank you.
Any other questions before I leave the entire topic of rail? There's a lot more in rail that I have in the notes that I'm not going to get into. I may come back to it if I have time at the end of the class, but unfortunately I doubt if I will, because I still have a lot of material to cover. So there's a whole section in the lectures for rail that I haven't had a chance to get to, that deals with how do you schedule inspections, ultrasonic inspections, that unfortunately I won't have time in this class to get into, but feel free to read ahead, and if you have any questions, send me an email. And I'll give you some good reference papers. There's some really good papers out there that describe how to use ultrasonic inspection, how to increase the number of ultrasonic inspections per year to match the increase in rail defects that you see with time, so that your risk of a derailment does not go up. So, okay, let's stop here. Let me go into my next presentation. Good, track train dynamics. Okay. All right, so now we're going to talk about track train dynamics. So just to get everybody's appetite going, I'm going to just give you a little derailment, and then we're going to use that as a walk-in to do that. This time I picked on a metro. This was a metro train that derailed in 2007 in Washington, D.C. This is Washington Metro. It occurred in an underground tunnel location. And as I indicated before, Metro is still happening. The train was traveling relatively slow at about 30 kilometers per hour. Now, the train consisted of 6 cars, but the 5th car was the first one derailed. So the first 4 cars went over the location where it derailed without a problem, which by the way, is not all that unusual in track train dynamics type of behavior. Now, in this particular case, 80 people were hospitalized. There was about $3.8 million worth of damage to the vehicle, so it was a little bit of a messy one. Those of you who know Washington Metro, it happened right over there. And this is a picture of what happens when you derail. What tends to happen when you derail underground in the metro is you hit the tunnel walls, and all of a sudden you get, even at low speeds, this was a low speed derailment, and it still caused $3.8 million worth of damage. As you see, when you smash into a concrete wall, it causes a fair bit of damage. So this particular one derailed at a turnout. The 5th vehicle derailed 3 out of its forward axis. It derailed on the curved portion of the turnout. It actually turned out to be so it derailed in the curved closure rail right over there. This is not, it was obviously underground, as you can see over here, but you can't see the layout of the tracks. I just want to show you there. So in this particular case, there was distinct wheel climb mark, characteristic of a wheel rising from the normal wheel rail interface. It was about 2 meters from the end of the switch point. Then there was a continuously mark on the top of the switch point. So what happened was there was a mark that showed the wheel going on top of the rail, about 2 meters from the end of the switch point. And then there was a continuous wheel marking on the top of the rail. So the wheel was running on top of the rail for a little while. And then it derailed about 8.5 meters north of the switch point. Typically, where it climbs the rail is not considered the derailment point. The derailment point is where it goes off the track. There are wheel marks in the gauge side of the track, etc. So there are all sorts of wheel marks. Now, one of the things that happened in this particular case, we're going to come back to this, but we already talked a little bit about Nadal equation, is that the wheels of the derail car were trued. So we haven't really spoken about wheel maintenance yet. That's something I sort of leave for the wheel part. But truing is a process by which when a wheel gets worn, so the flange gets very worn, I machine back, I come back and I machine a new wheel profile over here into the existing wheel. And I restore the thickness of the wheel flange, which is this dimension over here. And I can run that wheel now for another 30, 40, 50,000 miles or 100,000 kilometers or whatever, 50 to 100,000 kilometers, let's say. So the machine has been trued, which means it's been machined. And whenever you machine something, you always leave a little bit of a rough surface. So it means your coefficient of friction is high. So if you recall from the Nadal equation, and we'll show this again in a few moments, when the coefficient of friction is very high, you run the risk of your L over V threshold for wheel climb drops. Your risk of wheel climb increases. So for these newly trued wheels had a higher risk of wheel climb. In fact, when they inspected the wheel, let me get back to the highlight.
Excuse me, what is trued? What do you mean by trued? Yes.
Okay, I have a wheel, okay? This is a wheel profile, okay? After a while, the wheel wears. Usually it's flange wear is the biggest thing. So when the wheel flange gets too thin, I can't keep it in service anymore because it can pick a switch point. It can go in, it can force a switch point open. So what happens is either I have to throw the wheel away or I introduce a process called truing, which is a machining process. And when I true a wheel, I come in here and I machine away all this metal. It's actually going more like this. I'm going to machine away all this metal, and I'm going to end up with a new wheel profile further higher up. So my diameter of the wheel is smaller because I removed some metal, but it's still within my allowable range. And now I have a full profile, so I can now run the wheel. The process of machining that wheel is called truing. And it's a very standard procedure. Most railroads and most metros in the world do it. It's a fairly standard procedure for extending the life of wheels. So what happens is the truing process generated a very rough surface. That's this fish scale of points. Picture of that, yeah, right over here. So you can see, it looks a little bit like the grinding marks that I showed you earlier on the rail. This is almost a grinding, this is almost the equivalent of grinding, this is almost equivalent to grinding a wheel, except we're not using a grinding stone. We're using it's basically a machining process. So we're using a cutting tool to cut the metal off on the wheel. So we had this very high friction right over here, and it actually extends all the way down into the flange. So the high friction was all the way down here, and that contributed to that. Now, on top of everything else, these particular cars also had a derailment history due to the system of balancing the car leveling system. So in addition to every other problem they had, these cars also had a problem with leveling. So what a car leveling system does is it distributes the weight uniformly upon all wheels. So if I have a bogie with 4 wheels, I want to have 25% of the bogie load on each wheel evenly. And if I have if I have 8 wheels and a car, I want to have a uniform distribution of my load. So in this particular car, it wasn't quite leveling. It wasn't distributing the load evenly. And in fact, they found that the wheel loading was so bad that it was 20. It varied between where in a situation where it should have been 50-50 wheel loading, it was 25-75 instead of 50-50. So it was showing non-uniform loading. So this also contributed to this. So this was a case of a wheel rail dynamic behavior associated with 2 things: high L over V because of low V, because I had an unloading. So so if I have my L over V ratio, if my V is low, then my L over V is high. And then I had a low L over V through a wheel climb threshold because of the rough surface of the wheel, the high coefficient of friction. So this was a wheel climb derailment. And this is not unique to the United States. I'm not going to go through this because I don't really want to spend the time on it. But this is a diesel electric locomotive in the UK. that derailed on a curve. Again, because of high L over V forces. In this case, the lateral forces going around the curve were sufficient to cause the right-hand wheel to climb. And again, what happened here was high coefficient of friction on the rail, no lubrication. The wheel was reprofiled here too. So we had high coefficient of friction on the wheel and a relatively low angle of contact with the wheel and the rail because of the geometry of the wheel rail system in this particular case. So it was the exact same behavior. High L over V, though in this particular case, the high L over V was due to the high lateral forces and low L over V threshold. So again, I'm not going to spend time on it. It derailed on that on that curve. Again, pretty pictures. Again, wheel climb marks. Two sets of wheel climb marks. First one, 14 meters from the edge of the bridge. Second, 22. But here's what the wheel climb marks look like. You can actually see the flange of the wheel climbing on top of the railhead here. And then this is where it actually drops in. So it's running on the top of the railhead and then drops in. It drops into the field side. So you can see this is the gauge side. So this is where the wheel flange should be. It climbs up, runs into flange, runs on top of the railhead, and then it drops in on the field side and then derails. So again, the same cause. By the way, notice we're talking about Y over Q. Remember correctly, Y over Q is just a European way of saying L over V. So the immediate cause of that accident was high lateral forces. There was no check rail, so there was no guardrail. There was nothing that prevented from going across the derail. In fact, that was a finding of the British Railway Network Rail afterwards, that they should have had a check rail there. They didn't have it. High coefficient of friction, same issue we talked about before, which means low L over V threshold. Recent wheel profile, high coefficient of friction on the wheel, rough surface, low L over V threshold, low contact angle, wide gauge, or both are just generated in high lateral forces, high L over V. And so that takes me to the topic I want to spend the next hour on, which is track train dynamics. Track train dynamics refers to the interaction of different dynamic forces when a train moves over a track structure. It's very often related to the forces at the wheel rail interface, which we've been talking about. But it also includes broader vehicle motion as well. So track train dynamics really includes both the wheel rail interface and the vehicle track interface, and they are different. So let's take the WMATA case as an example. The wheel climb part of the WMATA accident was a case of wheel rail interface. So that was the Nadal behavior where the wheel was climbing the gauge face of the rail. Same thing with that British derailment, exactly the same thing. But there was another element in the WMATA system, and that was the car leveling system. And remember, the car leveling system was such that it did not uniformly distribute the vertical loads on all wheels, or had a non-uniform distributions. That in turn resulted in a rocking of the vehicle. So once we introduce that type of rocking of the vehicle, we have an issue that becomes very significant, and that is track train dynamics. That's the vehicle track interaction portion of track train dynamics. So because when you're introducing the rocking of the vehicle, you're away from the wheel rail interface, but you still have vehicle track interactions. Now, I will tell you that track train dynamics are really the derailments are usually the most difficult to diagnose. When we come back in January, I'll actually talk about derailment analysis in a little bit more detail. But I want to talk about track train dynamics here. They're difficult to diagnose because they often represent problems with both the vehicle and the track, or the wheel and the rail. Again, both the cases I showed you. In the case of the WMATA derailment, there was a high friction and there was a leveling system problem. In the British derailment I showed you, there was high rail friction, high wheel friction, so we had both of them, and then we had excessively large curbing forces, which was a vehicle track interaction rather than a wheel rail interaction type of problem. So very often track train dynamics is the one that there's no obvious failure, and it's very often a combination of effects. And very often this is where we have to use dynamic modeling to understand exactly what goes on. So there's a lot of computer simulation. This is where a lot of the wheel rail dynamic models, track train dynamic models were developed, such as Vampire and New Cars, to allow you to investigate this type of behavior. These type of occurrences can even occur when everything is within standards. This is one of the parts that bothers people. I was involved in a derailment in San Francisco, BART, where the track was in standards, the equipment was within standards, the operations were within the operating rules, everything was within standards. They were all within the edge. They were just on the edge of the standards, but they were all within standards. Yet the derailment took place. And that was because the interaction at the edge of the track and the equipment and the speed of operations was such that it generated sufficient track train dynamics. So that's an issue that we sometimes see as well. Okay, so I'm going to throw out a whole bunch of names to you, and then we're going to go through these in time. In fact, after the break, I'm going to show you a few movies to do this. So, but I'm going to give you a brief introduction here, and we'll go through it a little bit later. So these are 7 different types of track train dynamic derailments. Let's see what I have here. Okay, so let's keep going here. So I have wheel climb. Wheel climb occurs when my wheel is flanging the rail. Usually I have a very high coefficient of friction, either on the wheel or on the rail or both. And literally my flange climbs up the top of the rail, just like I showed you here. This is wheel climb. The flange is climbing up, 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 up. You can see till it's gotten to the top of the rail. That's wheel climb. And that's a wheel rail contact problem. Okay. Next one out of the chute is wheel lift. So wheel lift is different than wheel climb because it occurs when the flange is not in contact. So wheel lift occurs when there's some sort of rocking action. And we'll talk about different type of rocking action later, such as harmonic roll or dynamic roll. But it's a rocking action where think of the axle set rocking, so that this goes up, this comes down, this goes down, this goes up. And then obviously I'm going to get a lift. And if I lift and I go around the curve and I come back down and I come back on top of the wheel, or I come back, there's no rail there, then I have a derailment. So that's wheel lift. Rail rollover is when the forces, my L over V forces, are so high that they literally roll the rail over. Now they can be full rail rollover where it actually turns it over on its side, or it can be partial rail rollover where I rotate the rail sufficiently that the wheel flange drops down into the web of the rail, and all of a sudden I have my wheel running over here on the web of the rail, and that knocks the rail fully over. So that's rail rollover. A cousin of rail rollover is dynamic wide gauge, which occurs again. I have my lateral force. If those of you who want Y over Q, we can call it Y. And it causes the rail to rotate slightly. And for the gauge to widen. Once I rotate, this is pretty significant. This is about 75 millimeters, but it doesn't take that much. It can rotate, it can widen 25 millimeters, it can rotate 12 millimeters. If I'm in a situation where I have a lot of wheel wear and a lot of rail wear, and my axle set back to back is not that, is right at the edge of the fringe, I may only need 25 millimeters of dynamic gauge widening to drop in there. Next one is harmonic roll, also called rock and roll. That occurs when a wagon is going down the track and it starts seeing a series of battered low joints or battered welds, staggered. So in some parts of the world, my joints are parallel, they're opposite each other, which is very common in the UIC world. And in other parts of the world, the joints are staggered. That's the AAR world. We can have a whole separate discussion of why we do this, but this is primarily associated with the heavier axle loads, because you don't want to have two heavy axle loads coming down, two wheels with the same heavy axle load coming down on the same location. So we stagger. North American and AAR world staggers the joints. The European world, the UIC world, has them parallel. Okay, when my joints are staggered though, and I have battered, I can introduce a dynamic rocking into my vehicle. So as I go down the track, my vehicle starts rocking. And this is a resonance phenomenon. There's a critical resonance speed of the range of about 30 to 50 kilometers per hour. That's a critical speed zone for wagons that have bogie spacings that are about 15 to 20 meters. Actually a little less, about 10 to 12 meters. And so I generate a critical harmonic speed, I generate resonance phenomena, and I actually rock. In North American world, they call this phenomena rock and roll, because the vehicle is actually rolling. And that can generate derailments because the harmonics can be quite significant. So that happens with staggered joints. Pitch and bounce is a phenomena that occurs with square joints. So pitch and bounce happens if my track has my joints or my battered welds opposite each other. And what happens is now I take my wagon And I now rotate around the y-axis. So I'm now, my front is pitching and bouncing, my rear is pitching and bouncing. And again, this is another phenomena that we see we see this more in staggered joint type, in square joint type of applications with the joints opposite each other, but it's again a harmonic behavior where you resonate, you can resonate and generate this pitch bounce type of behavior. The last type of track train dynamics we're going to talk about is truck hunting. So truck hunting happens when my axle set going down the track moves dynamically from side to side. So literally it moves to the left and comes to the right, it comes to the left, it comes to the right. This is a different type of resonance phenomenon. So all three of these are resonance phenomena, harmonic resonance phenomena in three different planes. This is around the longitudinal axis of the track, this is around the lateral axis of the track, and this is laterally on each individual axle or bogie. So let's take a few minute break here because I have, let me see where my movies are.
Excuse me, Alan.
Yeah.
I didn't understand the wheel lift and the harmonic roll. Can you
Okay,
explain again?
let me see if I have a better picture of that. Okay, let me explain it again and then I'm going to show you. You'll actually see these in the movies I'm going to be showing you in a few moments, but let me explain it to make sure you're prepared. Okay, so wheel lift and harmonic roll are related to each other. So let's look at the end view of a wagon. So here's one rail. Here's another rail. Here's my axle. Here's my wheel. Here's my wheel. Okay, so if I have a series of staggered joints, I'm going to generate a rocking of my vehicle. Okay, so my vehicle is now rocking. It's coming down. First, it comes down on the right rail, then it lifts it, then it comes down on the left rail, then it comes down on the right rail. So it's rocking from side to side. Okay, that and this happens at a critical speed, and because it's excited by these staggered joints or staggered battered welds that generates this rocking action of the vehicle. Once the vehicle starts to rock, what happens at the wheel rail point is that this wheel will come up, then it'll come down, then it'll come up, and if it's in the up position, and if either the track moves or the vehicle moves laterally, it'll come back down top of the railhead. That's wheel lift. So this is harmonic roll and this is wheel lift. Is that clear?
Yes, thank you.
Okay. Let's take a brief break now. Come back about 22. I got a few more slides I want to talk about a little bit here, a couple of nice pictures. Then I have a series of 4 movies that were put together that I love these movies because they actually capture some of these phenomena in the movies. You'll actually be able to see some of these phenomena in the movie. So let's break. Let's take about a 12-minute break. Come back about 20 after, and we'll continue there.